Welcome to this pre-recording for a lecture on software in a course in computational geometry. This lecture is scheduled at the end of the first week of classes, lecture 3, scheduled for 17 January. So this is a new lecture in this course. In the previous two lectures, software was mentioned already, but kind of too quickly and kind of as a extra. Um, I felt that software is important enough to merit one entire lecture. So also to show that the field computational geometry has important and major software packages and is also available in general computer algebra softwares and software systems. And there's plenty of great software available. So the purpose of this lecture is kind of to give another overview of the field in computational geometry and also to give practical hints to get started. Um, so we have covered the convex hull problem as our first problem. That means the convex hull problem, not in complete generality, but we have seen the computation of the convex hull of point sets in the plane. So that was our beginning problem, and I will demonstrate four different packages or four different ways how to compute this. So the purpose of this lecture is that it may help to remove some of the confusion of the previous two lectures by focusing on one particular software package. If you try to commingle all four different ways that I'm going to show, it might again be confusing. But I hope that at least one of the methods will stick. Okay, just to start over again, so this is a computational course. In our MCS major, we have two tracks, algorithms and theory, and the computational track. This computational geometry sits on both tracks. It follows our course on algorithms, but it is also recommended for students taking the computational track. So by computational, we mean that we use software. So it's not doing computations by hand. That's often also what people mean by a computational course. No, we are using software to generate interesting examples and to study the properties of algorithms. When you are when you're studying an algorithm to solve a problem, as a computer scientist, you automatically always ask yourself, how is that now really working on a computer? If you're a programmer, you ask yourself the question, how can I make it work on a computer? But here we are already, because there is so much great software out there, we are going to use software to experience how the algorithms behave and look at some interesting examples. So it's relatively straightforward, especially also mainly beneficial if your drawing skills are not very good. It's after all a geometry course. So there are also excellent packages out there to visualize the geometric objects. Okay, in this lecture, I would like to present some of the important software. Also, another indicator that computational geometry is a very important field in computer science. So this is a mathematical course, but it's also a computer science course. I also hope to encourage you to get started. So there are computer projects in this course, and often one can do them in a little bit more than an afternoon and an evening. But don't wait till the day for the deadline to start experimenting with the software. Installing software can be extremely frustrating. Also, starting to use software can be extremely painful at times. So I hope that by starting early and doing it often, that we will have a very smooth transition from the theoretical concepts that we see in the class to having somewhere a practical understanding how everything really runs. So there are, in general, two types of software. Software that is available to us in a scripting environment. Python is, for many of us, a well-known programming language. Um, Python is often used as a shell or as an interface to compiled code. Um, so we will also actually compile C++ code. And we will mainly, this is again not a programming course, but we will be mainly running available test programs. Test programs provided in software libraries, and we will adjust those test programs, those top level programs, to whatever experiment we want to conduct. This is a university course. In academia, we prefer free and open source software. So also all software used in this course is free and open source. So I mentioned computer algebra systems, so there is also MATLAB. So we will not be using those commercial computer algebra system and MATLAB. Okay, there's plenty of good software out there. So the first software I should mention is ClickHull. The main result of the previous lecture is that we have demonstrated that the convex hull of points in the plane is essentially a sorting problem. N log n for n points is the cost. So the quick hull is actually very similar to the quicksort. So the first software, QHull, implements the general algorithm to compute convex hulls in any dimension. So we start in this course with the planar convex hull, and we kind of end, after more than 10 weeks, we kind of end with the three-dimensional convex hull problem. So it will become by then apparent that if you can compute convex hulls in any dimension, you can solve many geometrical problems. You can compute Delaunay triangulations and Voronoi diagrams and do many other things. So in some sense, this software, which was released in the middle of the 90s, kind of was one of the major results that make computational geometry in a really important field. The second software is CGAL, which is a very extensive library. It is a C++ library. So although there is also a Python interface which we will be using, which I will be introducing today, it is free and open source software. It is dual license, so there is also a company behind this. Again, the commercial viability of such software kind of illustrates the importance of computational geometry once again. Now, with geometry, you often not immediately associate scientific computing. So the third package, Triangle, I list here because it links with what is here introduced, so it appeared in a volume towards geometric engineering. It also won a very major prize in numerical software. So every 4 years, there is the society that awards the best a prize for the best numerical software. So computing triangulations is a very important problem also in the solution of partial differential equations when we look at when we apply finite element methods. So we will not go into that area at all, but just to make the connection that geometry applies to scientific computation just as well. So, and again, this is the computational track. So we may be studying triangle in a computer project. We will definitely spend 1 week on the Loney triangulations in this course. So for people on the computational track in our MCS major, they have taken numerical analysis at this point. Now, one also gets to partial differential equations. The efficient solution of partial differential equations also involves computational geometry. Okay, this is the big picture. Let's now try to make our hands dirty and look into how to get started. The first decision you have to make is, do I work in the cloud or do I install software on my own computer? The middle way is actually, do I have somewhere software in a computer lab on campus or on somewhere on a shared computer? So this is the middle way, which we may resort into for certain specialized software. Okay, but I will stick with these two alternatives here, the two possibilities, and it is an and or an or. You are welcome to try both. We will use mainly Python and the Jupyter notebook. So these are actually the two very basics. So we are assuming that one is familiar with the scripting language Python, Python as a scripting language. And I will show many examples of Jupyter notebooks. Jupyter, Julia, Python, R, and many others. So this notebook also actually essentially allows for language agnostic computing. It has become somehow a standard in um, scientific computing systems. Okay, in the cloud, one can use CoCalc, standing for collaborative calculation. This provides a free interface, so you have to sign up. The service is for free. If you are using it very extensively, I would recommend that you get a paying account. This gives you more compute time, and this could also give you installation, certain the requests that would be granted. SageMath is a free and open source system, and essentially it is a collection of many different free and open source scientific computing systems, all connected through Python. So Python is one of the advantages of Python is that it can be used as an interface language to glue many systems. First demonstration will be with SageMath. Okay, one can, and essentially I would recommend this if you have enough disk space on your computer, that you try to install the software. So this has major benefits. Now, of course, it can go wrong, so make sure that your operating system is up to date, especially with the security patches. If something, when you start downloading software, keep also track what software that you install, um, where you install it, when you install it, how you installed it. It looks kind of strange, but for myself, I actually keep files. It's very useful if you go from computer to computer. You have to install something on a similar computer. How did you do it a couple of years ago? installing software, unless you are a system administrator, installing software you do actually only once in a while. So it can go smooth, can be a smooth process, but it there are also so many choices, so many options that it's easy to get lost in the details. Okay, um, selecting the package managers. You could always install from source. So CGAL, the software that I will be introducing, has, or that I mentioned earlier, has a very nice GitHub, is hosted at GitHub. Most free and open source software has a GitHub home. Um, you The advantage of this is that you get to the latest software. The disadvantage is that it sometimes requires a little bit more expertise to install directly from source. Again, I mentioned operating system that should be up to date. Often it's also required that you have compilers that are up to date. Package managers may provide a much more smoother transitioning process. Um, okay, the disadvantage is that with a package manager, you may not have the latest software, but all software that we will be using in this course is very mature, and most likely there won't be much difference anymore with earlier versions and current versions. I mentioned the Python and the Jupyter notebook. All our homework, all the projects, all the exams will all be collected through Jupyter notebooks. Um, there is Jupyter in the cloud in CoCalc, but if you have to install it, I would recommend Miniconda. There is Anaconda. Looks like the name of a big snake, and it is big. So again, Miniconda is more minimalistic, and I would recommend starting with that. Linux systems have package managers. I'm using the package manager of Ubuntu. I'm doing this on Windows. So Windows for me has been more useful through the Windows subsystem for Linux. And of course, there is also the PowerShell, which is indeed quite powerful. I've also experience with Mac computers. There is the free and open source installation Brew. So Brew is a package manager that hosts a tremendous collection of packages. So if you buy a new Mac laptop, one of the first things I would recommend you installing would be Brew. Um, okay, so that's how we get started. So make your choice. Do you work on the cloud exclusively, mostly, or do you install software yourself? Again, we have deadlines in this course. You can make your project often the day before the deadline. You only need a day, and you could do this the day before the deadline, but don't certainly do not wait installing. So the most important exercise of this week is again to do some runs with software. Get yourself familiar, get yourself an account on CoCalc or install some software. And compute a planar convex hull. Okay, there we go. I mentioned as when you are a computer scientist, you always should be asking yourself, how does it really run on a computer? If you're a programmer, you ask yourself, how can I make this run on a computer? But we will be using software. There is the V representation and the H representation of a convex hull. They are very nicely available in SageMath, as I will introduce now. Okay, what is the what are the representations? Well, if you look at a polygon, and here we will be focusing on convex polygons. So any 2 points, if you connect them, all the points on the line segment are in the polygon. So think about the star. That's also a polygon, but not a convex polygon. So a representation of the convex hull can be defined as all possible line segments or all possible points on line segments between any 2 points in the set. That's what they call the V representation, the vertex representation. Alternatively, you can also look at a polygon as the intersection of half planes. So you can build a convex hull by making many convex combinations, or you can also start cutting away from the planes, splitting the plane repeatedly in halves. Everything that lies at the same half is contains one half in this H representation. H stands for the hyperplane representation. Hyperplane for general dimensions, but in the plane, uh, the half planes are bordered by lines that essentially extend the edges. Okay, so perhaps I was talking too much, and the example should make it clear. So in SageMath, SageMath provides a very high level interface. So you don't need to install it. Again, it runs on CoCalc. So here you see a computation. So I have a list of 10 points. In this list, so we say they are the vertices of a polyhedron. So polyhedron is a more general word of polygon. Often one says that a polyhedron may not be finite. So you could have a cone which stretches out all the way to infinity. Okay, here you see the random uh, point set, so the output, what SageMath plots. And then we have the example, or we have an example of a V representation and an H representation. So I start off with 10 points. As the picture showed on the previous slide, there are 4 corners. So that is the V representation. So P is the polyhedron. P dot V representation lists all the vertices. And SageMath is a symbolic, has a symbolic interface. So if you ask for the H representation, you obtain your inequalities. So here you see the inequalities that cut out this uh, polygon. So actually here it says that the equality, you have the um, I think I'm now a little bit confused. So the x here is actually represents the entire point. So you should read this inequality as 7 times the first coordinate x plus 4 times the second coordinate x. So x is actually to be seen as a point. Okay, this actually should be run in Jupyter Notebook, so I'm switching tabs here. So here I have a notebook, a Jupyter Notebook that runs in a kernel that is SageMath. So here you can see that it runs SageMath 10.3. So that's the version that I'm running here. Um, I generated this example on 20 July 2022, so that was my random seed of the day. So I will be always seeing the same data for the reproducibility. But perhaps I should comment this out. So let's look at another example. That will be the main benefit. So I will run all cells. So I generated 10 points. So here you see the x coordinates, you see the y coordinates. So the random number generators in SageMath are called here. I'm generating points with 2 decimal places between 10 and 99. So here you see the numbers. I'm making the list of the coordinates, and then you see the polygon. So I started again with 10 points, and you see I have 4 corners. And we see the equations. There's one that's actually, we see the vertices and we see the equations. So you kind of see that 39 is actually the lower edge. And you can see that there are 2 vertices at 39. So even with generating random 2-digit coordinates, I get actually a polygon where I have a horizontal edge. So you can see this horizontal edge here at 39. So the H representation gives us this equation. So the second coordinate minus 39 should be greater than or equal to 0. And you can see this also in the vertices. The second and the last vertex have actually the second coordinate 39. So this H representation represents the half planes represented by these inequalities. Convention here is larger or greater than. So we will say that we have minimum. So we have the minimum of all possible points. 39 is the lowest that you can get. And that lowest is attained at the endpoints of the edges. Here the edges with the second spanned by the second and the last vertex. So we have half planes determined by lines and essentially in an inequality. All other points, they actually lie above that uh, line, horizontal line with 39. So I hope that you get some feeling. So we started in this course with vector calculus. And what you have seen in vector calculus is how to set up equations of lines. Okay, so this is the first software, SageMath. So SageMath um, contains a lot of free and open source software packages, but Python as the gluing language. So Python has its own computational ecosystem. So the next example is with scipy, but scipy is actually also a component of SageMath, together with NumPy and Matplotlib. So the next computation you can also do on the cloud in Cocalc. But I will run it in a different notebook. Um, just to make the point, so SageMath can be a little bit overwhelming and perhaps too much for your needs. Um, SciPy contains the spatial package. And I mentioned before Delaunay triangulations, Voronoi diagrams, but here also convex hulls. And this is also a data structures course. It also contains queries that you can make geometric queries on uh, data stored in geometric data structures. There is ClickHall. You can of course run ClickHall directly. So if you go to this website, you can install ClickHall from there. But it is wrapped. It is available in SciPy. So let's do an example. So I will run this example as well. But this is a simple Python script. So you can run it. I ran it in a PowerShell of Windows. But it's nevertheless, I mean, and this is very condensed. So it kind of gives you the basic setup. I will also scroll through the Jupyter notebook, which has the advantage that it documents. So here you see also NumPy, SciPy, Matplotlib. When I have a new computer and install Python, I immediately install NumPy, SciPy, and Matplotlib, and also SymPy. So this is kind of the core of the computational ecosystem that you get with Python. So what do we do in this experiment? I generate 20 random points. So here I did not fix the seed. So we will see each time a different polygon. We list the vertices, we list the edges, and also there is a way to get to the equations. And it ends with a plot. So here you see the vertices, and this is only showing the print statements. So this is very minimalistic, but it only requires a terminal. So either the PowerShell or a terminal in a Linux installation. So with this example, here is what I obtained. So these are 20 points in the plane. So this is done with Matplotlib. Okay, so let me show the corresponding Jupyter notebook, which has the advantage that it documents things a little bit better. If you make a Jupyter notebook, we structure it so that it can be run as a computer program from top to bottom. Typically at the very top, you say what you're going to do with this Jupyter notebook, what is the purpose. And also it's typically good practice to have all the imports right at the beginning. So then actually you can see if you open the Jupyter notebook that you have downloaded from somewhere, do actually have the packages installed. So that first instruction will fail if your installation is not complete. Again, so this is running in a Jupyter notebook. I can't really show the kernel here as I did with the SageMath kernel, but this is now a Python kernel. So the computations in the previous notebook contains instructions suitable for execution by SageMath. The instructions, the code cells in this Jupyter notebook are to be executed by Python. Okay, first thing you see that this is a different world in the sense that we see floating point numbers. So NumPy is for array processing and linear algebra, mainly numerical linear algebra, using scipy and numpy requires some familiarity with numerical analysis. People on the computational track who have taken numerical analysis are familiar with this. But note that this may require often a little bit more attention. So there is exact computation with integers or rational numbers, and then there is approximate, dealing with approximate uh, input data, also with um, round off error. Okay, once you have the list of points, actually now here it is an array. So in the Python world, lists are very versatile data structures. In scientific computing, the array is the main data structure. Generated 20 points. You can see that of these 20 points, I have 8 vertices. So I get an index type back, a 13-bit integer. I can look at the coordinates in the vertices. So if I run over the indices, vertices, and I print the points. The points is the matrix, the 20 by 2 matrix that was generated. Okay, vertices and edges. So here we have 8 vertices and we also have 8 edges. Perhaps I should have pointed this out earlier, but we have exactly as many edges as we have vertices. So whenever you are programming things on your own, that's an important check that one must be aware of. So the edges are called simplices because the package actually can handle convex hulls in any dimension. So a simplex is a more general word for triangle. Simplex is a triangle in any dimension. The hyperplanes are defined by these triangles, the facets of the convex hull. But perhaps I should not explain this because it will take quite a while till we get to 3 dimensions. But we can also list the coordinates of these edges, the start point and the end point. So edge 0 starts with vertex 12, with point 12. We have only 8 vertices, with point 12 and ends at point 13. 12 and 13, you can see 12 and 13 are here, listed next to each other. Okay, so then the equations, and that's probably a little bit entirely different than if you remember the H representation with SageMath. It is actually also the H representation, but it is represented as an array, or you could say it is a matrix, an 8 by 3 matrix. And you may now wonder, wait, why 3 columns? I thought we were in 3D. But what you have is you have a normal, a vector that is perpendicular to the edge, and you have an offset. I will verify this. So the code here, so in some sense this is not programming, but this is scripting. So I'm assuming that everybody who uses software can actually write these simple checks. So again, I go over all the edges. So I mentioned that you can get the coordinates of the endpoint, so the start and the end values of the coordinates. Then I'm showing that the first edge will actually correspond to the first equation. So you can see that here we select from the equations the corresponding index. And then I said that we have the normal, the direction in which you actually look at this polygon. So the first two coordinates in that equations array are the coordinates of the vector. And you make the zero value at the edges. So you can see the first edge is perfectly nice, 0. Then actually you may wonder, you know what, on edge 1 I have numbers that are looking far from 0, but in scientific computing, in numerical analysis, we read the numbers from right to left because the numbers are typically represented in scientific notation. So we see that when we evaluate, when we are computing the inner product of the vector with the point and add the offset to it, we actually get something that is 10 to the power minus 17, 10 to the power minus 18, and that is below the machine precision. The double 64-bit precision that is provided into hardware. So this actually verified for the 8 edges, we have the 8 corresponding equations of the lines, and then also of the half planes. And then finally, we have the plot here. Notice that we addressed the robustness, so you can kind of see that some of the points are awfully close to edges. Well, probably the resolution of the plot is not that high. If you look at the coordinates, it may not matter all that much. But with the equations, you could kind of verify if there are actually points that are really close by who almost make it 0, but not yet quite. So these algorithms are robust, and it could be part of our project to examine the robustness. Okay, I'm 40 minutes in, actually 42 minutes, so this is scheduled for a lecture of 50 minutes, so I will have to speed up things a little bit. Although the last two are done with CGAL. And we have the CGAL swig bindings. So this is an interface that is generated from the code. From a programmer's perspective, this actually means that the Python interface is glued actually very tightly to the C++ code. The disadvantage I felt in using this interface is actually that you should look at the original documentation. So the documentation of the Python functions is actually not existent. They are documented, but then they are documented through the original code of CGAL, which, by the way, has a very extensive documentation, also tutorials. Okay, I installed, I think this with Conda, but you can also install it with pip. And the version that I installed is 5.6. I've been running this on the Ubuntu Windows subsystem for Linux, but it also runs in a PowerShell. The interface is still recent. I started using it in the last time that I taught this course in the fall of 2023. It contains almost everything that we will be needing in this course. So in some sense, if C++ is making you feel very uncomfortable, then don't worry. One can get around with Python. The installation process actually also works fine if you get Conda to work. Why wouldn't you? If then you can also install this. Okay, here is an example of a very simple example which I copied from the documentation. We are taking some points. Now we start from a list, but we have to use the data structure point underscore two. You see the imports, what we are doing. Then we compute the convex hull and we can print the vertices. So here it is. So I ran this in a very simple script. So we have the square, the unit square with some inner points, and the inner points are removed. So this runs in the command prompt. So actually I have two simple scripts. So let me run it. Convex 2D CGAL. There you are. And the script contains a little bit more which I cut off in because the slides were getting too dense. So one can also add a point. So if you add 2,2, then that actually will belong to the convex hull. It will be a new vertex. Okay. Finally, let's go to the C++ examples. So I installed the C++, I installed the C++ version of CGAL, or the original version of CGAL, with Ubuntu on the Windows subsystem for Linux. Here is the first thing that you can try. So there is the version.cpp. Here it is entirely listed. So you can check the version, what you have. And perhaps I should do this. So I have in, let me go to the version so I can type. Actually, what I do, I'm working with make files. So the make files make that I don't need to remember the instructions. So the Python Swig bindings, the CGAL Swig, the Swig CGAL bindings were 5.6. The package manager of Ubuntu has 5.4. I don't think there, from our perspective, there shouldn't be that much of a difference. Okay, final compilation is the construction of a convex hull. This looks more complicated, but actually not that much more than the Python scripts that we have seen. You have to be a little bit more aware of the using of the data structure. So here, instead of a list, we are initializing an array with 5 elements. So one has to be careful that in the declaration, so I'm making an array of 5 points of type point underscore 2, and then I'm listing them between these curly braces here. The results, and again, now it's actually important that you know that there are as many edges as you have vertices. So for the result actually will be also points. And one needs to work with pointers. So here you see the convex hull that takes on input the array points, the beginning and the end, and that returns the results. One can compute the number of points in the result. So this is what does get printed. And then we print all the points. And here is the output, essentially. What I point at is the minus LGMP. So we started out with SageMath, which by default, as a computer algebra, computes exactly. We went into scipy, which by default works with 64-bit doubles. And we now go to CGAL, where we are using extended software-driven precision in the GMP package. That's why I did not emphasize this, so I did not even mention it. So you have to make sure that you have the development versions of the GMP library. MPFR is another multi-precision library on top of GMP that is also being used by CGAL. You need the development version of CGAL that gives you all the header files. So these are the three installations. What was broken in the installation was the demos, and I had to download them separately from the CGAL home webpage, most likely also from the GitHub. Okay, I'm at the end. So the main conclusion is that we now have four different ways to compute planar convex hulls. They are listed here. It would be great if you could use all four of them, but at least try one of them. So this is the end of the first week. The main exercise is actually trying one of these computations. Okay, I hope that this was interesting, and I hope that this removes some of the confusion of the first two lectures, and that it also provides encouragements and guidance for the future development of computations.